Okay, so at the end of the last class, we were working. If you watched the video on Thursday, at the end of the Thursday class, we were dealing with that structure, and I asked everybody to draw a resonance structure. Okay, so I haven't covered resonance at all in class. We're going to do that now. Hopefully, you've watched the PowerPoints and read the books. So this will be a little bit of a mix of lecture and getting you guys to do stuff. So again, in this class, really any intellectual endeavor, there's got to be activity on your part, right? Learning is a physical process. Nobody ever talks about it like that, but your brain's got to actually do stuff. And you guys know, it's, a brain is not a muscle. You're not, actually moving when you use it. But to learn something, and you've all learned plenty of stuff, you have to be engaged. Right? If you just sit there and stare into space, it doesn't just seep into your brain. Okay, so I've drawn two molecules on the board. These are two molecules that you guys have seen, that are in the news. Right? We talked about water in class. Water is an incredibly important molecule, just sort of generally in chemistry, certainly in living organisms. Carbon dioxide also on Earth. Right? We eat plants, we eat carbon-based molecules, we oxidize those carbon-based molecules up to CO2 and we exhale. We produce CO2 a lot of other ways to negative effect. Okay, so what I'm going to ask you to do right now, one of those two molecules you cannot draw a resonance structure for, and the other one you can. So I want you to figure out which one you can draw a resonance structure for, and then draw at least one resonance structure. There's several, but draw at least one. I'll give you, 90 seconds or so. Which structure can you not draw a resonance structure?
H2O.
Can't draw a resonance structure of water. All right, so these are Lewis structures. Again, lone pairs or electrons are going to be indicated by dots. Bonds are going to be indicated by lines. A bond is two electrons. We're going to talk a little bit more about that here in a minute. But these two bonds are electrons. Hydrogen, of course, makes one bond, can only have two electrons. The second row elements are going to have an octet. The third row elements can have, a wide variety of numbers of electrons, which makes inorganic chemistry, we classify it organic and inorganic. Organic chemistry, it really does fit together coherently, and it's pretty straightforward. And, if you like to think about big picture stuff, like why is life on Earth carbon-based? I'm hedging my bets. We don't actually know if there's life elsewhere in the universe. I just don't, 50 years from now we discover there's life somewhere else and it's silicon-based and you come at me and want your money back or something. So, life on Earth is carbon-based, and there's no real way to answer this definitively, but if you think about what life is, right, we have to have a fairly organized system to process energy. So you can't have, like a rock isn't going to be alive, it just sits there. Right? So if you make a silicate, it just sits there, it's stable, nothing happens. That's not going to be life. But a lot of elements, and this is true of silicon, even silicon, like you just go one row down. This is a very popular science fiction thing, right? Silicon-based life. Silicon also makes 4 bonds. But silicon has electrons in the third shell, and it can make 5 bonds, it can make 6 bonds, and the geometries of those can be quite different. And then it can, if you get down to the end of it, if you exhale silica, right? SiO2 is a solid. It's hard to excrete that. CO2 is pretty easy to get rid of. You just exhale. So carbon is this, it's reactive, it does chemistry, but it's limited in how much chemistry it can do. And so you guys right now, you're just starting organic chemistry, it seems like there's this flood of information. But carbon really can't do lots of different chemistry, right? We did hybridization. There's sp carbons, sp2 carbons, and sp3 carbons. And that's basically it. Carbon can't really make a stable molecule with any other geometric arrangement. So carbon's, it can do some chemistry, but it's limited, so it can't just sort of adopt any conformation at once. Okay, so with that preamble, will hopefully get you interested. In water, in H2O, a resonance structure, so resonance structures will just be different Lewis structures that apply to the same molecule. All right, so this is a really important, I'll draw it here in a minute. I'll say it. A resonance structure for a molecule is just a different way of representing the same actual structure. We use resonance structures because of the limitation of Lewis structures. So before Gil Lewis, about 115 years ago, came up with Lewis structures, chemists drew molecules all sorts of different ways. We knew molecular formula, but we weren't real sure that structure really existed. Was it just a hodgepodge of atoms? Lewis figured out, hey, you can sort of make bonds, and it's, that water, so water Lewis structure works really well for. The Lewis structure of water applies to every molecule of water. But we quickly found molecules that Lewis structure didn't do a good job of describing. And this was at about the same time, there's an organic chemist named Linus Pauling who figured out hybridization and resonance structures. And what that really was sort of a qualitative estimate of what the physicists were doing, which was coming up with molecular orbital theory. Pauling's estimate was such a good qualitative tool that we still use it today in organic chemistry. I'll talk a little bit about molecular orbital theory. Those of you who become chemistry majors will need to know this really well. Those of you who don't, won't. Okay, so I'll try to stick with the qualitative theory as much as possible. So we've got carbon dioxide here. Obviously, process of elimination. If we can't draw Lewis resonance structure for water, carbon dioxide is the one we can draw resonance structures for. And I'll come back and talk about why we can't do water here in a minute. So there is a resonance structure for carbon dioxide where I take 2 of the double bonded electrons, right? The carbon and the oxygen have a double bond. They're sharing 4 electrons. So if I take 2 of those and I put them on the oxygen, I'm going to get this structure. So this curved arrow means 2 electrons go from the shared electrons to there to a lone pair. Right? If the carbon is neutral and I take 2 electrons away from it, it becomes positive. If the oxygen's neutral and I put 2 electrons on it, it's going to become negative. These are resonance structures. Right? The way we indicate 2 structures are resonance structures is with this double barb, one arrow that's got barbs at both ends. That does not mean equilibrium. And so here's the weird thing about resonance structures. This arrow doesn't mean CO2 drawn this way turns into CO2 drawn this way. What resonance means is both of those are valid Lewis structures for the same molecule. They both show some of the character and property of carbon dioxide. Right? So I use probably too many analogies. Sometimes they're good. If I use an analogy and it doesn't work for you, just ignore it. But this is basically, like saying, never mind. This is better for confirmations later. But there's multiple different ways of saying the same things. Like, you are more than one thing. A photograph of you does not represent all of them. Okay, so carbon dioxide, we can also take, we could take 2 electrons from this other double bond, and now we're going to have a doubly plus. I guess really I should draw the electrons here. All right, that's also a resonance structure of carbon dioxide. Using a green arrow, we can have we take a lone pair on the oxygen, have it use that lone pair to make a third bond to the plus carbon. So this is also a resonance structure. Right, these are a lot of resonance structures for carbon dioxide. Carbon dioxide is a pretty simple molecule, and yet it's got all these different resonance structures. So now, which one of these is the best structure? Which one do you think best represents carbon dioxide? Why? Right. So, the best resonance structures are going to, if you have a molecule for which you've got to draw more than one Lewis structure, sorry, let me back up. If you've got a molecule for which more than one Lewis structure can be drawn, the best Lewis structure is going to be the one that minimizes formal charge, it gives all the atoms a full octet, if you have to have charge, right? So if you've got to have formal charges, right, we've got a plus and a minus. You would like to have those closer together. It's hard to see this one in CO2, but if you have a longer molecule, where you could have resonance structures that have the charges right next to each other, or separated by a few atoms, or separated by a few more atoms, the one that has the charges closer will be better. Can you see this word on the, you guys on the right-hand side of the room? See that word? Okay. All right, if an atom has to lack an octet, right? If to draw a resonance structure, you have to have an atom that doesn't have a full octet. You want that atom to be the least electronegative atom. Okay, there are also, for example, I'm going to draw this and I'll probably erase it really quickly. We could move these 2 electrons from the carbon-oxygen double bond onto the carbon. The blue structure I just drew on the left, the middle left-hand board, that is also a resonance structure of carbon dioxide. It's a stupendously crappy resonance structure of carbon dioxide. Right? The most electronegative atom lacks a full octet. The least electronegative atom has a negative charge. Right? If carbon and oxygen are sharing electrons, if they decide to stop sharing electrons, the carbon's not getting those electrons. Right? The more electronegative atom is going to take the electron. So here's the other thing. Like if I just ask the question, like draw a resonance structure for carbon dioxide, that works. You can also split electrons up. All right, that's a resonance structure of carbon dioxide. Carbon gets one electron, the oxygen gets one electron. Those are now radicals. A radical is an atom with a single unpaired electron. And they're neutral. This carbon's neutral, that oxygen's neutral. So you might think, oh, that's pretty good. But you would like to keep the electrons paired if you can. So here's the other big thing about resonance structures. And this is hard at your stage. Right? The good resonance structures will represent something about the real structure or the real property of the molecule. Right, if you think about it like clothes, this is more or less how I look most of the time. I don't often wear nice pants. I wear just a nice enough shirt to get by. I also sometimes wear sweatpants and a t-shirt. That's not a bad resonance structure, right? You will find me that way a lot. You can also imagine me in, a $3,000 suit and a tie and everything's pressed. That is a bad resonance structure. You will rarely find me that way. Okay, so these two resonance structures, it turns out, actually don't represent anything about the real property of the molecule. If you look at carbon dioxide, there's a significant partial positive charge on the carbon and a partial negative charge on the oxygen. The molecule is symmetric, so the overall dipole of carbon dioxide is 0. The dipole of both carbon-oxygen bonds cancel. But that carbon does chemistry where it behaves like it's positively charged. The oxygens do chemistry where they behave like they're negatively charged. So these resonance structures, even this one with a 2+ carbon, this is not a good resonance structure, right? Every atom's got a charge, you got a 2+ carbon, that's not a good resonance structure. But that is better than these, because the carbon's positive, the oxygen's negative. So it sort of behaves like the real molecule. This one's going to be the best one. You got the charges closer together. The electronegative atoms have full octets. Illustrates the chemistry. The green one over here is not so great. Not awful, but it's got the charges separated. Right? So some of that, at this point for you guys, that's maybe a little tougher to judge because we haven't done a lot of reactions yet. We haven't looked at a lot of properties of molecules. So you have to know a little something about the molecule. Right? If you didn't know me and you just saw a picture of me dressed in, an expensive suit, like I am now, and in essentially pajamas, you would have no idea which better represented me. Right? Get to spend an hour with me and you'll rule the suit out. Okay, so I need to notice. Can I see it? Fine, yeah. All right, so I'm going to erase these bad ones. there's a couple of other things that have to be true. Resonance structures, again, I can't say this enough. Resonance structures are just different ways of drawing the same molecule. They all exist simultaneously. The better the structure is, sorry, I've got a crease in my mask. The better a resonance structure is, when I say better, the more stable, right? So for carbon dioxide, this purple one I drew first, that's the better one. All the atoms are neutral, they all have the full octet. So the molecule looks more like that one than the others. But the others don't, it's not like every now and then the molecule looks like one of the others. It always has that property in it. Okay, so this blue structure is always there, just a little bit, adding a little flavor. Makes the molecule react that way. Makes it, react like a positive carbon and a negative oxygen. So if they have to be connected the same, or if they have to be representing the same molecule, then the atoms have to all be connected the same. Right? So you can't move an oxygen here or take a hydrogen off. They all have to have the same molecular formula, the same conductivity, same overall charge. Right? So the original structure, the purple structure, is neutral. All the atoms have a formal charge of 0. They're all neutral. The blue structure has a +1 and a -1. That's 0. The green structure has a plus and a minus. That's 0. The black structure has a 2+ and 2 -1s. That's 0. Okay, so you can't have, a molecule can't simultaneously be neutral and negative, or neutral and positive. You have to have the same overall charge. And then this comes, that flows out of that. If all the atoms are connected the same and they all have the same overall, the two structures have the same overall charge, you're going to end up with the same number of electrons overall. So when you draw resonance structures, double check this. Make sure you don't move atoms. So you will never break a sigma bond, it turns out. So let's talk about bonding a little bit. All right, a covalent bond, I've said, is 2 shared electrons. But there's a few different ways to do that. And what it really is, right, it's 2 electrons in a bonding molecular orbital. Like I said, I'm going to try not to dive too deep into molecular orbital theory. Molecular orbital theory is just the theory of how atomic orbitals from all the atoms in a molecule mix together to make molecular orbitals. So you guys from Gen Chem know, right, 1s, 2s, 2p, 2p3, there are 3 2p's, 3s, 3p, 3d, so on. Those are atomic orbitals. And those orbitals exist independent of whether there are electrons there, right? Hydrogen has a 5f orbital. It just rarely has electrons in it. Okay, so molecular orbitals exist the same way. There are molecular orbitals that don't have electrons in them, but they're a place for an electron to go. If an electron is in a molecule, it's in a molecular orbital. Okay, it actually gets pretty complex how these orbitals get created, and the best way to know them is through mathematics. Right? I'm not qualified to teach anyone differential equations. I'm barely able to do differential equations anymore. If you don't use it, you lose it. Okay? So I'm an organic chemist. I don't have to solve differential equations. So I'm not as good at it as I used to be. all of what we're doing here, Lewis theories, Lewis structure, is an approximation. It's a qualitative way to get at the reality of molecular orbital theory. And it works really well. It works almost perfectly well some of the times. Water here, the Lewis structure of water is bang on. All right, you can use Lewis theory and basically nail the structure of water. And what you might notice, for resonance structures to exist, you need some combination of lone pairs and pi bonds. Okay, so for resonance structures, to need to be able to draw resonance structures, to need to consider resonance structures for a molecular structure, you've got to have pi bonds, or charges, or lone pairs, all close enough together. Remember, what we're doing, all we're moving is electrons. The only thing that moves between resonance structures is electrons. Right? So they have to have somewhere to go. Right? I can't look at carbon dioxide and just say, well, I'm going to take this lone pair and I'll put it on the carbon. The carbon then would have more than 8 electrons, so you can't just do that. So there's got to be a flow to it. All right, so how do we get a bond? Let's think about the H2 molecule. Lewis structure of H2 is just an H sigma bonded to an H. And you guys have probably seen this, right? You got two 1s orbitals. They each have 1 electron. They come together. You can, mathematically, orbitals behave like waves. The equations that describe orbitals are the equations of waves. So if these mix, they have phase. So if we take 2 hydrogens, we take the 1s orbitals together, we add them together in phase, we get one big molecular orbital that we call a sigma orbital. Each hydrogen brings 1 electron with it. So those 2 electrons go in the sigma bonding molecular orbital. We get a sigma bond. We get a molecule. All right? I'm throwing a whole... Most of this stuff you're writing down, you're not going to have to directly reproduce. All right? I'm just trying to explain why it happens. Electrons are more stable generally when they have more space to fill. So the bigger an orbital is, the more stable it is. The more stable the electrons in that will be. Make sense? So a bonding molecular orbital is, by definition, it occupies more space, has more volume than the individual atomic orbitals by themselves. Well, it turns out there's also a way we can